Hello and good afternoon friends, welcome to CEC-UGC live lecture. Dear friends, as you know that since yesterday we have been talking on our series on chemical reactivity and mechanism, and under this series yesterday we talked about carbon cations as well as their chemical reactivity. Today also we are going to touch this area, that is chemical reactivity and mechanism, and under this today we are going to discuss carbanion. For this we have again with us in our studios Mrs. Vandana. She is assistant professor in Dayal Singh College, Department of Chemistry, Delhi University. So first of all I would like to welcome our guest Mrs. Vandana, and I hope all the students who might be benefited from yesterday's lecture would be benefited from today's lecture also. So ma'am, welcome to the EDUCET lecture, and as I said that the students would be benefited, especially the students of chemistry who might sometimes skip some of the important things during their classes. I hope they would be able to recall all the things what they have missed. So over to you ma'am.
Thank you Gitika for a nice introduction, and you are very right that chemical reactivity and mechanism is the important part of undergraduate students. In the series of chemical reactivity and mechanism, today we will discuss about the carbanions and their reactivity, chemical reactions of carbanion. Carbanions are the reaction intermediates formed in the reaction, and we will also discuss about their generation, reactions, their stability, effect of substituent, enol and enolate reaction with the carbonyl. Carbanion forms in the reaction as the reaction intermediates and then come to the product. What are carbanions? Carbanion is an anion in which carbon has an unshared pair of electrons. As we know that carbanion form in a reaction after heterolytic cleavage, and it bears a negative charge usually with 3 substituent of a total of 8 valence electron. So what is the exceptional thing in this intermediate? However, there are many reaction intermediates in a reaction, carbocation, carbanion, carbene 19, but this is the only intermediate which is having complete octet, means 8 electrons. The carbanion exists in a trigonal pyramidal geometry. How can a carbanion generate, and what will be the fate of carbanions? This can be generated by 2 ways. A group attached to a carbon leaves without its electron pair. The leaving group is most often a proton. It is an acid-base reaction, and other leaving group also known. Second, when a negative ion adds to a carbon-carbon double bond or triple bond. Here you can see the example of double bond alkene, and the addition of a negative ion to a carbon-oxygen double bond does not give a carbanion, since the negative charge resides on the oxygen. So how can we prepare the carbanion? When a negative ion adds to olefin. Now the reactions of carbanions. Carbanion combines to a positive species, commonly proton, because it is negatively charged species, or another species that has an empty orbital in its outer shell. Second reaction, carbanion may proceed by, it may form a bond with carbon that already has 4 bonds by displacing one of the 4 groups. In the earlier lecture we were discuss about the SN2 reaction, bimolecular substitution nucleophilic, when we got a intermediate pentavalent transition state. Third reaction which may generally observe with the carbanions intermediate is it can add to the carbonyl carbon. And fourth one which is rarely observed is the rearrangement of carbanions. Now what is the stability of carbanions? A carbanion is a nucleophile. The stability and the reactivity of nucleophile is determined by several factors. Number 1, inductive effect. Electronegative atom adjacent to the charge will stabilize the charge. Number 2, hybridization of the charge bearing atom. The greater the S character of the charge bearing atom, the more stable the anion. Third, the extent of conjugation of anion, resonance effect can stabilize the anion. This is especially true when the anion is stabilized as a result of aromaticity. We will discuss in detail in the coming slides. Number 1, the effect of substituent on the carbanion stability, hybridization. What is hybridization? Hybridization is the mixing of orbital of unequal energy to give orbitals of same energy and same shape. So this is hybridization. It affects the stability of carbanion. How it affects? In almost all areas of organometallic chemistry, the primary subdivision of reactivity types is by the hybridization of carbon and metal atom. A key subdivision is the presence of conjugated substituent. We all know what is conjugation. Conjugation is alternate single and double bond. The fractional S character of the CH bonds. What is S character? In hybridization, the portion of S is known as S character of the CH bond has a major effect on the kinetic and thermodynamic acidity of the carbon acid. Only S character have electron density at the nucleus, and a lone pair with high fractional S character has its electron density at the nucleus, closer to the nucleus, and stabilize. This can be easily seen in the gas phase acidity of prototypical CH types, ethane, ethylene and acetylene. Here you can see the hybridization effect and S character, how it varies in the carbanion stability. Corresponding carbanions shown below, the negative charge resides on the carbon atom that are respectively sp3 hybridized, sp2 hybridized and sp hybridized. You can see ethyl carbanion, ethenide carbanion, acetylide carbanion. And first carbanion is sp3 hybridized, ethenide carbanion is sp2 hybridized, while acetylide carbanion is sp hybridized because of triple bond. Since the electronegativity of the carbon increases with increasing S character of the bonding, that is in the order of sp3, sp2 and sp, the carbanion stability will follow the same trend. What is inductive effect on the carbanion stability? Electron withdrawing substituent will inductively stabilize negative charge. You can see the many examples in the slides that there are atoms like sulfur who has electron withdrawing capacity. These effects are complex since electronegative substituents interact with the carbanions in other ways. Oxygen and fluorine also have lone pair and which tend to destabilize adjacent carbanion. Conjugation, delocalization, pi delocalization. What is pi delocalization? We know in a conjugated system there is a delocalization because of pi electrons. Delocalization of negative charge, especially onto electronegative atoms, provides potent stabilization of carbanionic centers. We also observe this kind of delocalization in carbocations. Since almost all conjugated substances are also more electronegative than hydrogen or methyl group, that is CH3, there is usually a significant inductive contribution to the stabilization, not only in case of carbanion but also in case of carbocation. Here are some examples in which we can see that there is a pi delocalization. We have already said that what is delocalization or conjugation. Conjugation is known as the alternate single double bond, and delocalization is in the conjugated system. A special case is the aromatic stabilization of cyclopentadienide and related indenide and fluorinide anions, which follow the Huckel's rule. For a compound to be aromatic, you need to follow the Huckel's rule. And what is Huckel's rule? It is the 4n plus 2 pi electrons for a cyclic system. One of the most versatile carbanion intermediate, namely the enolate. with their utility in various carbon-carbon bond formations being central issues. So, in the carbonyl reactions, we are taking importantly the enolate ion. What are enols and enolate anions? The process whereby a hydrogen atom to the alpha carbon atom of the carbonyl group moves to the carbonyl oxygen atom is known as enolization or keto-enol tautomerism. The isomeric carbonyl and enol structures are tautomers. The extent of enolization is dependent on the acidity of a proton. More acidic the alpha proton, more probable the enolization, and hence equilibrium constant for tautomerization, keto-enol tautomerization will be higher. Normally the carbonyl carbon is favored, however structure factors can significantly affect the keto-enol tautomerism. In the reaction you can see the keto-enol tautomerism in ketone. In the presence of base, the first structure shows the keto form, while the second structure by the hydride shift shows the enol form. So basically is the enolate ion. The interconversion between the keto and enol form is catalyzed by both acid and base. This is very important because in aqueous solution rapid protonation of carbonyl group occurs first, which is followed by removal of alpha proton by water in the rate controlling step leading to the enol. So you can see here in the reaction that acetone, when attacked by water molecule, there is a formation of enol form by the removal of alpha proton. Under basic condition we have discussed about the acid condition. Now under basic condition, abstraction of alpha hydrogen. This is the quality of base to abstract the alpha hydrogen atom. And the initial rate controlling step, proton abstract from the solvent completes the enolization process. Here you can see the reaction of keto-enol tautomerism with the help of base. Kinetic and thermodynamic enolates. Generation of enolates of ketone is at times challenging because they pose a problem in regioselectivity. Ketones can have enolized protons on both sides of carbonyl groups. The problem is not so much when one side of the ketone does not have the enolizable proton. For example, in case of acetophenone or ketone is symmetrical, the real issue is with the unsymmetrical ketones, whereas enolizable protons are present on either side. So for successful reaction we need to control which side enolate should be formed. If one of the proton is significantly more acidic, the selective enolate formation is straightforward. For example, in the case of ethyl acetoacetate, there are two types of enolizable protons. However, only one type of two protons is deprotonated first. Which one is more acidic? This is an example of thermodynamical control. Only the more stable of the two possible enolate is formed. You can see in the reaction that there is a more stable enolate ion and less stable enolate ion. This principle can be extended further where the difference in the acidity of the protons on either side is not as pronounced. Example, 2-methyl cyclohexanol, there are two enolates which are possible as shown. Now enols and enolates are alkene and hence the more substituted it is more stable LVB. So when equilibrium is possible, the more stable enolate will form. This is possible if the proton source is unavailable. In this case, a slight excess of ketone itself can act as a source of proton. So today we will discuss an emphasis on the carbonyl compounds with enolate. So first reaction we are taking here aldol condensation. What is aldol condensation? A aldehyde or ketone that has alpha hydrogen next to the carbonyl group. A hydrogen can form an enolate in basic solution, hence enolate can react by nucleophilic addition at the carbonyl group of another molecule. The process is very important synthetic procedure and is known as aldol condensation, and the final product from aliphatic aldehydes or ketones against both a carbonyl and an alcohol group. The product is known as aldol. You can see the reaction. What is aldol condensation? When aldehydes or ketones reacts with base to give an aldol. Here you can see the reaction of aldol condensation, the mechanism of aldol condensation in case of aldehyde and in case of ketone. What is happening in the mechanism? The base will first abstract the alpha proton from the aldehyde and from the carbanion. This carbanion will attack the first reactant, and then we will have an intermediate which will lose the proton and form the aldol, beta hydroxyaldehyde. The product is beta hydroxyaldehyde. Similarly, in case of ketone, you can see cyclic ketone first of all attacked by the base. Here is abstraction of proton from the alpha position, and then this carbanion will attack to the second molecule, and then by reaction with the water molecule we will get the again product aldol, beta hydroxyaldehyde. Examples of aldol condensation containing aldehydes and ketones. The aldol products react readily with acid to undergo dehydration. After aldol formation, what is aldol? Beta hydroxyaldehyde. It will undergo dehydration and give alpha beta unsaturated carbonyl compound. What are alpha beta unsaturated carbonyl compound? These are very useful in synthetic, organic and biological chemistry. Basically, alpha and beta related to the positions carbonyl group. Intramolecular aldol condensation are useful in the formation of cyclic alpha beta unsaturated ketones. Here you can say there is a cyclization of molecule and we will get alpha beta unsaturated ketones. Cross aldol condensation. What is cross aldol condensation? In which a aldehyde reacts with ketone. In cross aldol condensation, enolate can react with another aldehyde of different structure. The requirement is that the other aldehyde has to be more reactive than the first, and it contains no alpha hydrogen. For example, formaldehyde. So when a aldehyde having alpha hydrogen, the simple aldol condensation will take place, and when there is no alpha hydrogen, the cross aldol condensation will take place. Formaldehyde and benzaldehyde both meet these requirements and useful in this procedure. As we know, formaldehyde and benzaldehyde both are not having alpha hydrogen, because in the formaldehyde adjacent to carbonyl there is CH bond, and in benzaldehyde adjacent to carbonyl group there is a phenyl ring. So no alpha hydrogen is there. So cross aldol condensation will take place. All three of the alpha hydrogen in acetaldehyde can react in a cross aldol condensation with the formaldehyde. The mechanism will be same. The base will attract the proton, abstract the proton, then formation of carbanion. The carbanion will attack on the another molecule and we will get the intermediate. That intermediate will lose the proton molecule and will give the beta hydroxyaldehyde. Aromatic ketones bearing alpha hydrogen give aldol reaction product readily, but in this case the aldol product spontaneously loses water to form the unsaturated ketone. So here is problem to obtain the aldol product, but in spite of aldol we are getting here the alkene, unsaturated ketone. When benzaldehyde is used in the cross aldol condensation, the final product is the unsaturated aldehyde or ketone. Conjugation of the double bond with the aromatic ring is the reason for spontaneous dehydration. The carbanion of ethyl fluoroacetate reacts readily with benzaldehyde in a cross aldol condensation to give the fluorinated alcohol. Alpha fluorinated carbonyl compounds are often very toxic material because biologically they are converted to fluoroacetate, and we know fluorine atom is very reactive, which has to be toxic to the Krebs cycles. Thus extreme care is needed when using these compounds. Claisen condensation. What is Claisen condensation? Esters like aldehydes and ketones give an aldol type reaction. When the alpha hydrogen of ester is removed by base to give the enolate, The enolate reacts with another molecule of the ester in an addition-elimination reaction characteristic of esters, which appear as displacement of the alkoxide. The resulting product here is a beta keto ester, and the reaction is known as Claisen condensation reaction. Here you can see the mechanism of Claisen condensation reaction. The ethoxide base first of all abstract the proton, alpha proton from the carbonyl group, and then it attacks the second reactant, and we will get a intermediate which will rearranges to give the beta keto ester. Why beta? Because the position of keto group to the ester is beta. Claisen condensation, again the alpha hydrogen in the product beta keto ester are more acidic than the alpha hydrogen in the starting ester, because thus a new enolate is formed and that is more stable than the first enolate, thus helping the reaction go to the completion. Mechanism will be the same, with abstraction of proton, attacking of carbanion to the second reactant, and then reaction with acid to give the beta keto ester. What is cross Claisen condensation? Occurs when a highly reactive ester with no alpha hydrogen react with enolate derived from another ester. Ethyl benzoate and ethyl formate are the two frequently used esters having no alpha hydrogen. Here again there is a abstraction of alpha proton, then this carbanion will attack on the another formamate and intermediate, followed by hydrolysis. You will get the product beta keto ester. Claisen condensation of ethyl benzoate with ethyl acetate affords ethyl benzoyl acetate in the crossed Claisen method. Intramolecular, you know the term intramolecular refers to the within the molecular. Intramolecular means within the molecule. Claisen condensation go by the name of Dickmann condensation and are useful for preparation of 5 and 6 member rings. Ethyl fluoroacetate reacts readily in a crossed Claisen condensation reaction with diethyl carbonate to give the diethyl fluoromalonate. Diethyl fluoromalonate can be used synthetically just as diethyl malonate. And you can see in the Dickmann condensation reaction there is a cyclization. First of all, the ethoxide ion will abstract the proton, and then the proton negative charge developed at the carbon will attack on the carbonyl carbon of the ester group, and hence there is a cyclization of the ring. Enolate anion alkylation reactions, general reaction, when strong anhydrous bases such as sodium hydride, sodamide or lithium diethylamide are used to prepare enolate anions at low temperature. The resulting enolate reacts very slowly with carbonyl groups and can be used as nucleophile. All the carbanions used as nucleophile in the SN2 reaction with the primary alkyl halides. In the resonance stabilized enolate, a negative charge exists on the both carbon and an oxygen atom. Both sides are possible nucleophiles in the reaction, but the carbon nucleophile predominates because it is a stronger nucleophile but minor products from orthoalkylation. So you can see when reacts with methyl iodide, the major product from the negative charge on the both carbon and on oxygen. Alkylation of the carboxyl amine of the fluoroacetone show temperature dependent regioselectivity. Alkylation of simple fluoroketones seems to be little. Mixtures are found, but the major isomer shown is produced in about 90% yield. Imines are used because there is no competition for aldol type additions. Fluorinated dihydro-1,3-oxazine below is alkylated easily with benzyl bromide. After reduction and hydrolysis, a fluoroaldehyde is obtained. And this is a fluoromodification of Mayer synthesis. In Mayer synthesis, the dihydro-1,3-oxazine derivatives are alkylated, and this is the modification. Alkylation of ethyl acetoacetate and diethyl malonate. Beta ketoester have earned a special space in organic chemistry for their value as compound used in the synthesis of new carbon-carbon bonds. We all know the importance of ethyl acetoacetate and diethyl malonate in industries. The general method for their involves the formation of enolate between the carbonyl groups, reaction of the enolate in an SN2 reaction with an alkyl halide, and removal of one of the carbonyl group by decarboxylation. What is decarboxylation? Removal of carbon dioxide. The result is the formation of methyl ketones or acetic acid derivatives. Here you can see the reaction ethyl acetoacetate. When reacts with base will abstract the proton from CH2. Why only CH2? There are other groups also like CH3 at the left hand side terminal and CH2CH3 at the right hand side terminal, but the abstraction from the CH2 at the middle only, because these hydrogen atoms are more acidic. Why they are more acidic? Basically the ethyl acetoacetate and diethyl malonate reactivity totally depends on the acidic hydrogen. What are acidic hydrogen? The central hydrogens. They are more acidic than other hydrogen atoms because of presence of electron withdrawing group adjacent to the CH2 group. So here base will abstract the proton from the center hydrogen only and we get a carbanion. This carbanion will attack the another molecule and alkylation will take place. The alkylation of ethyl acetoacetate and diethyl malonate. You can see in the reaction that ethoxide ion C2H5O negative is the ethoxide ion. It will abstract the proton. I have already told that the more acidic proton, the abstract will be more easy. Then there is a formation of carbanion. It will attach to the another molecule, followed by protonation and decarboxylation. We will get the product. Here this substituted acetone. The decarboxylation occurs readily because it proceeds through a favorable cyclic transition state as shown below. You can see there is a decarboxylation and the cyclic transition state is followed. Double alkylation of ethyl acetoacetate in sequential step can provide a synthesis of highly branched derivatives of acetone after the hydrolysis and decarboxylation steps. What is the importance of this reaction? Is that if you want to introduce any alkyl group, you can easily introduce. Because there is acidic hydrogen, you can easily replace the acidic hydrogen of the center by the mechanism 3 steps. Number 1, removal of acidic proton by the base, then attack of this alkyl group. Whichever alkyl group you want to introduce, you have to take that alkyl halide, and then there is a hydrolysis, acidic hydrolysis or ketonic hydrolysis. If you done ketonic hydrolysis, you will get the product ketone. If you do the ketonic hydrolysis, ketone product will be there. Acidic hydrolysis, acid will be product. So this is the basic concept behind this. You can introduce any kind of alkyl group to these acidic protons, and it has its own importance in the industries. Diethyl malonate also possesses acidic alpha hydrogens and may be used instead of ethyl acetoacetate in the above sequence. As we have taken ethyl acetoacetate, we can also take diethyl malonate instead of ethyl acetoacetic. The difference is found in the final product that contains an acidic acid structure unit instead of acetone. The Michael reaction. What is Michael reaction? There is a 1,4 addition of enolate ion. Olefins on their own are not very good partners in the reaction with the nucleophiles, and we know that carbanions are nucleophiles. So they are very good acceptors, but when conjugated with electron withdrawing group. What are electron withdrawing group? When a group is having electronegative atom like carbonyl in aldehydes, ketones, ester, amides, nitriles, aldehyde, ketone, ester, amides, acid, the derivatives all are having carbonyl group, undergo addition of nucleophiles rather easily. The resonance structure, you can see the resonance structure of alpha beta unsaturated carbonyl compound. Alpha beta unsaturated means that this is the position related to the carbonyl compound, and you can see the resonance structure. There are two resonance structure for alpha beta unsaturated carbonyl compounds. Resonance structure of this type of compounds reveals the fact that beta carbon is electron deficient. Why it is electron deficient? Because of attachment of carbonyl group, and oxygen being electronegative comparatively to carbon attract the pi electron towards itself, hence made this carbon alpha beta carbon positively electron deficient. When it is electron deficient, the nucleophile will attack on this position. When addition of nucleophile proceed with such a mode, it is commonly referred to as 1,4 addition. You can see in the reaction that the arrow shows the electronegative character of oxygen with comparison to the carbon, and the nucleophile attacks on the electron deficient carbon. This type of 1,4 or conjugate, I have already told you what is conjugation, alternate single double bond. Conjugation, addition of carbanion or its equivalent to alpha beta unsaturated compound is commonly known as Michael reaction. Very important reaction. Many alpha beta unsaturated carbonyl systems may be prepared by dehydration of aldol products. Examples of the Michael reaction using methyl vinyl ketone and acryl nitrile, two common units in the reaction are shown below. Enamine additions. Enamines, the product of acid catalyzed addition of secondary amines to aldehydes or ketones. In the reaction, you can see there is a attack of secondary amines to the aldehydes and form the enamine. Enamine will react with the alpha beta unsaturated carbonyl system in the Michael reaction. In this method, it permits the introduction of new carbon-carbon double bond. So, if you want to introduce a carbon-carbon double bond, you can take the help of enamine addition with Michael reaction adjacent to the carbonyl group. Robinson ring forming reaction. It is a unique reaction that produces a new ring containing an alpha beta unsaturated ketone. It means there is a alpha beta unsaturated carbonyl group as well as new ring is formed. When an enolate derived from a ketone reacts with methyl vinyl ketone, the enolate adds in the Michael reaction. Then a second enolate in the ketone product is formed that cyclizes in an aldol condensation to give the final product. So, you can see that in the Robinson reaction, alpha beta unsaturated carbonyl ring with the ring formed is formed. The diethane system is capable of stabilizing the carbanion by dispersal of charge into the d orbitals of sulfur atoms. When the diethane carbanion is used as nucleophile, the diethane unit can be hydrolyzed to carbonyl group. You can see the resonance structure of diethane system. As sulfur is having d orbitals, there is a delocalization of negative charge and hydrolysis to carbonyl group. Organometallics compound. What are organometallic compounds? Generally, whenever we talk about organometallics, the first point come in our mind is RMgX. The formula for organometallic compound is RMgX. R, any alkyl group, magnesium is metal, and X is halide ion. With comparison to the magnesium metal, the alkyl group is electronegative. So, this is the beauty of organometallics compound and used in the industries. Because of this reason, the metal Mg has electropositive character comparatively to R group. Organometallic reagents are well known in organic chemistry. The Grignard reagent, RMgX are known as Grignard reagent. Rather than Grignard reagent, there are other organometallic compounds in which magnesium metal ion is replaced For example, organolithium reagent, organozinc reagent are the used as nucleophiles in the addition to the carbonyl groups in SN2 reaction and in Michael reaction. A few examples of their counterpart in the organofluorine are shown here. And the trifluoromethyl anion is prepared by reaction of trifluoromethyl trimethylsilane with fluoride ion. The strong affinity of fluoride ion for silane drives this reaction toward the trifluoromethyl anion, and the anion addition to a carbonyl group is shown. So here you can see the carbanion is trifluorocarbon. Trifluoromethyl carbon shows good ability as coupling reagent with aryl aromatics. Trifluorovinyl lithium is produced from chlorotrifluoroethane and butyl lithium. The lithium reagent adds easily to carbonyl groups. Reformatsky reaction. Instead of forming the enolate from an alpha hydrogen, which we have discussed in the diethyl malolate and acetoacetic ester, here an alpha bromine atom can also be used. That is what is known as Reformatsky reaction. Zinc metal is used here, reacts with ethyl alpha bromoacetate to form a zinc enolate that reacts at the carbonyl function of aldehydes and ketone to produce alpha beta hydroxy ester. The method is made either by addition of bromoester to a mixture of zinc and then carbonyl compound. Here the mechanism of Reformatsky reaction. First of all, the zinc atom will react to the alpha bromoacetate to form a zinc enolate. This zinc enolate will attach to the carbon aldehydes or ketones, followed by hydrolysis to produce alpha beta hydroxy ester. Ethyl bromo difluoroacetate is used frequently in Reformatsky processes to give high yield of alcohol products. Keto-enol equilibrium. Ketones can exist as two So this is the summary. Ketones can exist as two equilibrated molecules. One molecule is the often written ketone structure, while the other structure is a tautomer known as an enol. In some cases, the enol contribution can be large. When fluorine atoms are present in the ring, the electron withdrawn by fluorine around the carbonyl increases the positive charge at the carbonyl. The molecule responds by forming the enol. So basically, keto-enol tautomerism depends on the equilibrium. Here are some structure keto-enol tautomerism. Rearrangement. Next, rearrangement of carbanions, homoallylic rearrangement. You can see the structure below represent the allylic, homoallylic and homobenzylic. What does it mean homo? There is an additional carbon atom. Some interesting rearrangement occurs with the homoallylic system. The examples below show a homobenzylic rearrangement where the carbanion interacts with the aromatic ring. Homobenzylic rearrangement. The carbanion appears to be insert. There is an insertion of carbanion in the benzene ring containing the 2-methyl group. The mechanism of the rearrangement is proven by the isolation of cyclopropane. Here you can see in the second step there is a formation of cyclopropane after the insertion of carbanion in the benzene ring, and when a paraphenyl group is present. So you can see the mechanism in this slide. Thank you so much.
With this note, thank you ma'am, thank you so very much for explaining us in detail what carbanions are and how the chemical reactivity takes place. Now in between the lecture I have noted some terms which students might be known or might not be known. So we would be discussing on what those terms are. In a general one-line definition, what could we say about the term hybridization which you used?
Hybridization is the mixing of orbitals of slightly different energy, slight shape, to give the orbitals of same size and same energy. For example, if we take the example of sp3 hybridization, there is a mixing of s orbital and p3 orbital. P3 are pxy, py, pz, mixing of these orbitals to give the sp3 hybrid orbitals. So we are taking the atomic orbitals, then there is a hybridization, and the after hybridization we will get the hybrid orbitals. So the number of hybrid orbitals will equal S1, P3, total 4, and we will get the 4 hybrid orbitals, sp3.
And what is that inductive effect which you introduced in your lecture today?
Inductive effect depends on the electronegativity of the atom. If in the carbonyl group, there is a electronegativity difference in these two atoms, carbon and oxygen. So oxygen is more electronegative than the carbon atom, so it pulls the bonded pi electron towards itself. This is the inductive effect.
When does a double bond forms between a carbon? When we say that there is a double bond formation, is there anything criteria for that?
Actually, you might have deduct from the
lecture
Claisen condensation that when there is a product, the beta hydroxy ester, but when we heat it, there is a elimination of water molecule, and we will get the alpha beta unsaturated product.
And what is the term alkylation which you used?
Alkylation is the introduction of alkyl group in any reactant. Any alkyl group like CH3, methyl group, C2H5, simple, these are ethyl, methyl, or any alkyl group.
And enols and enolate ions which you explained?
Enolate ion I have explained in my slides, that keto-enol tautomerism. What is it? Keto-enol tautomerism depends on the equilibrium, and there is a transfer of proton from keto to the enol form.
And beta keto esters?
Beta keto ester, beta means the position related to the ester. Ester group, first carbon adjacent to the ester group is alpha, second carbon is the beta.
If we talk about esters in a general term, what basically esters are?
Esters are the compounds which is having the molecular formula simply RCOOR. Carbonyl group and ester RCOOR. These are the molecular formula. R can be alkyl group, R can be aryl group.
And O is for the?
Oxygen.
O is for oxygen. That means that they basically combine with the carbon.
Yes, they are combined with the covalent bond.
Basically with the covalent bond.
There is a covalent bond.
And covalent bonds are the double bond formation?
Covalent bond after sharing of the electrons between the two atoms.
Between the two atoms. You also described about organometallics. What organometallics are?
Organometallic compounds generally, first of all, the organometallic compounds point come in our mind is RMGX, Grignard reagent. But rather than RMGX, Grignard reagent, there are magnesium compound Grignard reagent, but zinc metal is also there, lithium metal is also there. Organometallic compounds are very important in industries because of the beauty of that magnesium, lithium or zinc. All these atoms are electropositive atoms, and comparatively to R group, they are heavy electropositivity, so there is a formation of carbanion on alkyl group. This is the beauty of organometallics compound.
While talking about the reactions, as we discussed in this lecture also today, the reformatory reactions, what kind of these reactions are?
In Reformatsky reaction, basically the alpha beta, okay. The beauty of this reaction is this, that a particular metal is taken, zinc is taken here, and first of all there is a enolate from alpha hydrogen, and alpha bromine atom can also be used, and the product is alpha beta hydroxy ester. Main thing is that zinc atom is used here.
After this Reformatsky reaction, I am asking continuously all those terms which you have used in the lecture, and my basic objective is all the students who might be watching us could recall again through the questions. Now ma'am, you used this condensation, that is cleansing condensation. Please explain us if possible.
Basically condensation is related to if in any reaction there is a elimination of small molecules like water molecules, like carbon dioxide molecules. This elimination of small molecules related to the condensation. And Claisen condensation, here in Claisen condensation, the alpha hydrogen in the product beta ester are more acidic than alpha hydrogen. What is actually happen in the Claisen condensation, that the ethyl acetoacetate, the acidic proton will be removed by base, and then there is an introduction of any alkyl group, and the product is beta ketoester. The main reaction is related to the product.
Likewise, I also wanted to ask you, what is the Michael reaction as you used in this lecture today?
In Michael reaction, there is a 1,4 addition of enolate ion and introduction of alkyl group takes place.
Generally, we talk about acetones very much when we talk about this form of chemistry. What basically acetones are?
Acetone has the formula CH3COCH3, ketone group is there and 2 alkyl group is there.
Thank you, ma'am. Thank you so very much. And I hope that this glossary at the end would help the students lot to recall, because sometimes while going through the lecture, it is not able to concentrate on every aspect. But I hope you might have grabbed a lot through this lecture. And in future also, Mrs. Vandana would be with us, and we will be continuing our this lecture on chemical reactivity and mechanism. And under this, we are going to cater numerous topics. Thank you, ma'am. Thank you so very much for being with us, and thank you for this productive lecture.
Thank you so much.